Well, hello everyone. This is Miguel, and I'm going to present my master thesis on the design and development of the bias in adversarial networks for toxicity detection in social media. My supervisor at IIT has been Professor Kai Shu. I've also counted with the support of my supervisor at UPM, Jose Maria del Alamo, and also PhD Yu Chin Liang has been my supervisor too. Here's the outline we're going to speak about today. I have first prepared an introduction and the objectives of my project. Then we're going to speak a little bit more about the literature review, key concepts, and related work that has been done in the state of the art. Then we're going to speak about the methodology and the data that we've used to make our project work. Finally, we're gonna end up with some results that we've achieved. We're gonna mention the conclusions, limitations, and future work that we've detected, and we will finalize with the acknowledgement session, which I think it's important because this work has been quite supported. Okay, starting with the introduction, this project covers fairness and bias in machine learning in the context of toxicity detection in social media. Fairness and bias, and especially biased models can amplify society biases. This means, for example, that we can end up having racist AIs, like for example, Microsoft's AI, which was basically a bot that answers tweets, and basically it was learning by reinforcement learning, and it became a racist algorithm. But it can be in a lot of different ways. I've just remarked this one, but it can appear in content recommendation, in advertisements, and in the one that we're gonna treat today, which is toxicity detection in social media. An example of a biased algorithm in toxicity detection is, for example, an algorithm that is gonna predict as toxic every comment that is written by women, for example, or by a collective which is sensitive, like with the sensitive attributes. Also, we're going to combine all these with a real world case scenario, which is going to join another line of research that I've been working on, and which is a study of how the US Senate is behaving currently on Twitter. And this kind of combination is going to provide valuable real world knowledge about the working of the US politics, and also we're gonna incorporate with this real world data set with known actors. So we're gonna put a name and a last name to the authors of the tweets. It's important to say that this other line of research has been accepted in ICML 2023, and we presented it in Honolulu in person in the Latinx in AI workshop. So to conclude this slide, the basic objective of this thesis is to develop fair adversarial neural networks for toxicity detection in real-world scenarios. And also, in addition, we're going to compare that to a reference model that we will speak about later. Continuing with the introduction, I put here a set of questions that our project aimed to answer, and in the end, it was possible to do it. Like, for example, obviously, what are fairness and bias? How can a machine learning model end up being unfair and biased? What is the state of the art? How good are adversarial architectures generating fair models? Also, what improvements in accuracy and fairness can be achieved by incorporating the bias in adversarial networks? And finally, how our models have been performing not only in the theory, but also in the real world scenario that we were speaking about with the US Senate. In this presentation, I might cover all of them, but if there's details that aren't clear, the report covers them widely. Okay, so once we're done with the introduction, then we have the literature review, and we have some key concepts that I want them to be clear. First, bias, which is a set of systematic errors or deviation in the model predictions that favor or disfavor certain individuals or groups based on demographic attributes, like, for example, as I was speaking, gender or race or age, for example. Fairness also consists on ensuring the absence of unjust or discriminatory treatment in model predictions, which are closely related, but the big difference is that bias is related to the design and the data used to train a model that can result in different performance, while fairness is related to how these benefits of the model are distributed among different groups. I also put here a diagram of the actors and causes of bias. There's three main actors that can be biased, which is the users, the data, and the algorithm, and they are connected with these lines that state how these bias can be transmitted. You know, like users generate data, this data trains the algorithm, and also the algorithm makes decision. So this is how or what the causes of bias are. Again, this is widely developed in the report, and you can read that for further information. And I also relate what types of causes can be and what types of bias there are. Well, so following, we have how to measure fairness, which is another key concept. So we need to know how fair are our models, how unbiased they are. The literature review covers a lot of metrics. I've explained them in my report, and I've chosen demographic parity and equalized odds to measure the fairness of my models. Demographic parity measures if the proportions of toxicity detected are the same among groups, and equalized odds doesn't measure the proportions, but measures the accuracy among groups. So basically, the idea is that we have to treat all groups exactly the same independently of which group they are. So the ideal scenario is that I'm going to be as accurate in, for example, male comments and female comments, which is equality of odds. And I am also going to detect same amount of toxicity among male than women, which is demographic parity. So that will be the main idea behind these two metrics. So continuing with the literature review, and after showing how these fairness metrics can be solved, we have what's toxicity detection, because this is the other key concept that we have. So toxicity detection is the identifying and flagging posts, comments, or messages that exhibit harmful or offensive behavior. Okay. And we have three main stakeholders in this process. The first one is the industry, Twitter, Facebook, TikTok, all these platforms that they have hosting all this toxic content. Then we have academia, which must help the industry in order to improve their techniques. And finally, we have the regulator. We have the regulator has to punish this toxic behavior of the users. So in the first actor, the industry, I had the opportunity to talk with a meta AI researcher in toxicity detection in ICML. He told me about the toxic users approach that they're having, and which basically what they do is that they usually score users according to their toxicity. And obviously, if you have a connection with a toxic user, you're more likely to be toxic than someone who hasn't got any connection with toxic users. And that's a really scalable approach, because you're trying to measure your network as a graph, and you're avoiding to treat all the content, which is a much higher volume of data. But other things that have been done is obviously to employ vast amounts of human resources in content moderators that are reading manually the content or watching it, and then they're flagging it. Then we have keyword filtering that can lead to these biases that we're treating. For example, if we associate some kind of words, for example, I don't know, female or black, if we associate those words with toxicity, then we're going to end up with biased models. Then obviously we have user reporting. In every social media, you have the opportunity to flag content that you think it's harmful or it's offensive, but then this can lead to attacks to certain accounts, so it's obviously not infallible. And finally, we have machine learning algorithms that obviously every industry has. I wanted also to comment that Google is the one who works more, as far as I've read, in terms of toxicity with Meta. And also Twitter has a free speech policy, and it's very complicated to see comments flagged by toxicity because they're almost inexistent. Academia, on the other side, is working on deep learning models and also in graph neural networks, basically on the same line of the industry. But also I found a couple of interesting jobs in how demonstrated how the context didn't improve classifiers detecting toxicity, and also another one which treated toxicity as a pandemic, which is something really important because they demonstrated that if I am a toxic user, I am more likely to expand, to spread those toxicity among my friends. And if you're my friend, you're more likely to be toxic if I am toxic. And that goes in line with what I spoke with my colleague in meta. And finally, the regulator has to act again to punish these behaviors, and it's important to remark that the European Union has the DSA, which is a specific regulation to avoid this kind of behavior and to punish it. And finally, the US doesn't have a specific regulation on it, but the Supreme Court has said that this toxicity regulation is under the First Amendment law. So obviously there's a methodology to make toxicity detection unbiased and fair, which is debiasing methods. Debiasing methods are all the technologies or the methodologies that we've employed to make fair models, and they are cataloged into 4 main branches according to Otavio Parraga, which I think is a very accurate classification. The first one is distributional approaches, which are the ones that we use before training. Then we have one-step training methodologies in which adversarial networks are involved or are in this branch because they involve just a single process of optimization in which we're going to optimize at the same time bias and performance metrics. Then we have the two-step training methods, that they involve a first step of optimizing bias and a second step of optimizing performance with a fixed bias. And finally, we have inferential techniques that don't involve any optimization in their process. To continue, we have the reference models that we've found as interesting to our project, and we're actually going to use just the first one, which is the Toxify. It's a model that was trained on the Jigsaw unbiased dataset competition, and it was developed by Unitary AI. It's an open source model, large language model. It's pre-trained and found in Hugging Face. And then we have also Perspective API, which is the commercial tool official used by companies like the New York Times, and it's the one provided by the Jigsaw group, which is the privacy detection group of Google. Well, continuing, we have the methodology. After speaking about the important parts of the literature, obviously this is a wide section in my report, so we didn't cover all, but we tried to cover the key concepts in order to understand the global scope of the project. So the datasets that we've used are these ones. The first one is the Jigsaw dataset. The Jigsaw dataset is a dataset that is made from the social media civil comments. This is a social media that shut down in 2017, and they made all the comments public. And then Google took them and labeled them, and also they added the sensitive attributes, ending up in what you see on screen, which is 2 datasets that we've split, having 2 sensitive attributes. One is race and the other one is gender. As you can observe, also there's a certain imbalance in toxicity, which is normal because in real world scenarios we have an imbalance on the data, and obviously there's much more non-toxic content and less toxic content. But in terms of the gender, more or less the proportion between male and female are okay, and they're a little bit unbalanced, but okay in the race dataset. And finally, we have the US dataset, which is the one that I collected previously. It is a much bigger one with almost 250,000 samples, and in this case, we feel a big imbalance on the sensitive attributes, which is also spread to the Senate. It's important to remark that we don't have the labels in the US Senate dataset because obviously we're not Google, and we use this to try to test the behavior of the models in the real world, but obviously we don't have performance metrics on them. So continuing, we're gonna explain a little bit more which architecture we've designed. So basically, as we've mentioned before, this is an adversarial network, and an adversarial network could be treated as a black box, like in this image, in which you can observe that there's a text coming in, and the model is gonna predict the toxicity and the sensitive attribute, which is gonna be, in one case, male, female, in other case, black or white. So we're gonna make a combination of both outcomes in order to train again the model. So diving a little bit into the model, we're gonna see that it's divided into 2 main parts, and at the same time, one of the parts is divided into 2. So basically, one is the unit of toxicity detection, which could be an independent classifier, and that's why it is in a green box. And then you have the adversary, which is gonna try to cheat on the training of this adversarial network in order to make this model unfair. It's important to say also that the classifier and the adversary share the same input, which is made with an encoder. And this part can also be assumed as a large language model, which is fine-tuned to our task. And we're going to see that in the next slide. As you can observe, the green box is now a bigger box. Then we would have here the encoder. The text would enter here. This encoder is a pre-trained model downloaded from Hugging Face that has a tokenizer and obviously the encoder. And we basically transform a text input into a vector embedding. And this vector embedding is the one that we feed to the classifier and the adversary. Also, this diagram is a little bit more complicated, so I'm going to spend more time in explaining it. The classifier would output toxic, non-toxic, and the adversary would output this. So what we are going to do is to calculate the loss, because these two things are scored between 0 and 1. So we calculate the loss, which is the distance obviously to our two labels, and we combine it to get a final total loss, which you can observe is the classifier's loss minus lambda times the adversarial loss. This lambda is one of the key concepts of this project, and we're going to backpropagate all these loss to the model. Note, importantly, it's important to know that we're not going to backpropagate this loss to the adversary, and we're going to just backpropagate the adversarial loss. Why this? Because in this case, what we're going to do is we're going to minimize the classifier loss, but if we minimize the negative adversarial loss, what we're going to do is to maximize the adversarial loss. And obviously, after each iteration, we don't want our adversary to get worse. We need him to get better in order to try to make this training process a little bit more complicated. So this is basically the functioning of our architecture, and what we're going to change is the adversary, the classifier, and the encoder. The adversary is less important for our presentation, but it's well detailed in the report. But I wanted to fix to point out these two different architectures that we've proposed that are here mentioned. In the first case, we've tried a distilled-bird language model with a feed-forward classifier, which is a simpler architecture, and also we've tried with a bird-based uncased and a CNN classifier. And also we've trained these two in the Jigsaw dataset. That means that we've trained this one first on the gender and the race, and this one first on the gender and the race, ending up in 4 different models. So after explaining the methodology, we end up with the results. The first part that I want to say in the results is that since we've done a huge experimentation, I wanted to make a small index in this point. The first thing that we did was to test the reference model on the Jigsaw dataset. Obviously, we wanted our architectures to be compared against something, and this something is the reference model, which is, reminder, it's the detoxify from Unitary AI. So once we get these reference metrics, we know if our models are doing great or are doing bad. So how do we train our models? Well, we select and optimize certain hyperparameters on our architectures, and especially the lambda that I was talking about. We need to, this lambda, what does is basically it sets the influence of the adversarial loss in the total loss. So the bigger lambda would mean more hard debiasing, but it would also fall into what it means big decay of the performance of the model. So we need to fix this lambda in order to end up with a classifier that is fair but also performs well. Then we choose the optimal architectures and compare them to the reference model. You will see that we end up with a table of our best possible results with each architecture, and those results are going to be compared to the reference model. And in the end, we're going to see how these models converge in the real world scenario of the US Senate dataset. So this slide, what does is to present the results of the reference model. Obviously, without any comparison, you won't know if these are good or are bad. But I can say that obviously the F1 sounds good for both cases because a 70% in toxicity detection is really well, specifically because toxicity is kind of a subjective task, and that means that it's easy and likely to fail not only models but humans. You can also observe that the loss in the race dataset is bigger than in the gender dataset, and that means that obviously this task is going to be more complicated. And you can also see that it's more likely to have bias on the race dataset rather than on the gender dataset, because once again, fairness metrics, the important thing is to minimize them because the proportions have to be equal, and that equal is 0. So continuing, again, what I did was the lambda selection. Basically, the training that I've performed is first select a certain set of lambdas and then try train these models with these lambdas. So the conclusion is that for each lambda, it takes a couple or 3 hours to train a model. So I've trained 4 models 5 times with lambda 0.01, 0.1, 1, 10, and 100. That means that I've trained 32 different models, taking a lot of time. But the insight that I want to showcase here is that, okay, the blue line, the blue straight line is the reference model. So the idea is that in the left we have the performance, in the right we have the fairness. The performance, you can observe that the loss is much lower in the reference model than in our different architectures with this hyperparameter selected. Also, you can observe here some inconsistencies due to a high lambda. And in terms of F1, again, we are far away from the model. But the good point is that in terms of demographic parity and equality of odds, we clearly overcome the reference model, which means that our models are much fairer. Well, in this case, our model with the distilled and feed-forward architecture is much fairer than the reference model. So basically, after watching these graphs, what we do is that we select a certain amount of epochs of training with certain lambda, which in this case is lambda 1. Okay, let's follow with the next training, which is the distilled architecture with a feed-forward classifier again against the race dataset. I was stating before that the results were gonna be worse because the race dataset is a more difficult task to do than the gender classifier, and you can observe that the pattern is the same in this case. You can see that the loss is much worse in our case than in the reference model. Obviously, this is double than in the previous slide, and you can see that in our case it's also bigger. But also, in our defense, we can say that our F1 is closer in this case in the race dataset, which means that our models cut a little bit the difference in this dataset, and also the big difference is found on the demographic parity, where our debiasing architectures are working properly and they are reducing a lot the bias of our models. And finally, we have the bird-based case architecture, which was trained against the gender dataset. And in this case, you can observe that the differences in fairness are much lower, which means that this model is a little bit worse in terms of fairness, and also we are far away again in performance metrics. It's important to say that we didn't find a good adversary in the bird-based architecture, so we basically ended up discarding this experiment, and instead of 4 models we ended up having 3. Okay, the reference model has these metrics, and also we have these 2 architectures provided by us in gender and race. So basically, watching the loss, you can observe that in the gender the loss is much lower, and obviously, okay, just to remark, obviously these ones are our optimal architectures. In terms of loss, we are far away, same for the F1, even though the difference is not that big, but in terms of demographic parity, you can see that the difference is gigantic. It's 7 times in terms of the race. It's a little bit lower in terms of the gender, not that case in terms of this architecture. But the equality of odds, it's also, again, half in this case, a little bit lower in this case. So our models are much better in terms of fairness and are a little bit worse in terms of performance, because we can observe that there's a trade-off between fairness and performance. And finally, here I just put the optimal threshold, which you can observe. It's a little bit different between models. The threshold is basically a metric or a parameter that measures in what score we're gonna start to flag a comment as toxic. So in this case, we would need less to see that a comment is toxic than in this one. So our last experiment was in the US dataset, in the real world scenario that I told you, and we've followed two approaches. So the first one is to focus on the flag comments. Important to remark that we have less than 1% of toxicity in all the models. That means that even the model that detected the most amount of toxic comments, it was less than a 1% of the dataset, which reminder, it was almost 250,000 tweets, which speaks well about the US Senate behavior. It means that the US is not behaving toxically. And well, this figure, it's important to see how the agreement is made. So what we can observe is that the distilled architecture, in terms of they have a better percentage of agreement, and also they are closer to the reference model. Meanwhile, the birth gender architecture is a little bit far away from everyone. You can observe that when these models flag something as toxic, only a 50% of the cases the birth gender also flags it. So we could observe this disagreement between the birth gender and the rest of the models. Also, a little bit of visuals. I wanted to showcase which are the most important words that come when it comes to toxicity. And basically, you can observe that some of the most important words are pathetic, or hell, or jobs, or Putin, or hypocrisy, which are usually associated and would defend the theory of keyword filtering, but still, it's important to get to them by using deep learning models. And finally, focusing on the parties, we can observe that there's more agreement between models. In the top 5 of senators flagged, you can observe that there's a common winner in all, and more or less there are the same names for all. And finally, focusing on the party toxicity, we can see that the Republicans are a little bit more toxic according to the 4 models, with the lowest difference measured by the reference model, but also we can observe that the levels are quite similar, which says that our models are, even though our performance might be lower in terms of theoretical data, we see that there's certain kind of agreement, specifically in the distilled architecture. So that was all for the results, and we're gonna end up with the conclusion. This slide basically summarizes what we found. In terms of the conclusion, our results have overcome the state of the art in fairness. There's also a trade-off that we've observed between the performance and the fairness, and we've situated ourselves in a point in which we are taking more into account fairness than the reference models. And also, we've tested these models in a real-world scenario, which is something that I consider key in order to see how good these are in real-world deployment. So as limitation, obviously, there's an impact on performance that we've measured. Our models are not as good as the reference model in terms of performance, that's for sure, but also we are better in terms of fairness. There's also a lack of data. Our data is from 2017. It's been almost 4 years since that, so 7 years since that, and obviously there's new trends in toxicity, and we cannot get to that point. Also, we have a lack of labeled data. As again, the latest toxic data labeled in huge amounts is that Jigsaw dataset, and our dataset is not labeled. We just can label the gender and the race of the authors, and also we can also have room for improvement in fairness metrics. And finally, as future lines, I wanted to try a double adversarial network, which is a network that reduces bias in both gender and race. That would be a great option. I wanted also to include perspective AI as a future line, and also an adversarial cross-validation, which is to try to see how good our model optimized in gender performs in the race dataset and vice versa. And as a last part, I wanted to add a section of acknowledgements because I consider that it's important to to mention that our thesis was published in the Latinx in AI workshop. It was granted by the organization, and I could go with my Congress paid, and also I was granted with the scholarship Connect Our Research, and I was able to engage IIT and UPM Research Lab in this research project, and probably this built new relationship between universities, and this work was helpful for it. And also I acknowledge the help of both universities in order to make this thesis. So thank you very much. I hope you enjoyed my presentation, and don't hesitate to contact me if you need any more guidance on this matter of devising adversarial networks.